Okay, I will type the function p of n is equal to 1 minus. Okay, I have the numerator, which is, I will use parentheses, 365 factorial divided by 365 minus n factorial. Okay, that's upstairs, and downstairs is, just for safety, I'm using parentheses. It's not necessary. 365 to the nth power. Okay, that's the function here. Okay, now let's do cases that we know. When you're alone, what's the probability that you share birthday with somebody else in the room? 0, of course. Let's do another case that we know. When there are 365 people, what's the probability that, let's make 266. What is the probability that 2 people will share the same birthday? 1, for sure, because, you have one more person than there are a number of days in the year. But the interesting thing happens, like when there are 50, for example. 50 people in the room, what's the probability that 2 will share the same birthday? You get this horrendous fraction that we cannot just make heads or tails. So we'll force decimal from Mathematica by giving 1 point, 0. You don't need the 0, but that's the idea. So I will redefine the function so that it gives me the, actually I could have just put 50 dot also, but here we go. There's 97% chance that 2 people will share the same birthday when there are 50 people in the room. It's virtually guaranteed. Isn't it amazing? What if you had 100 people in the room? Then what would be the probability? Well, it's practically 1 already. It's 1/3 of the number of days in the year. Still, it's that high. What if you had 40 people in the room? It's already 90%. I mean, when do you reach 90%? When you have 41 people in the room, you have 90% chance that they will share the same birthday. This is very, very intriguing. I hope you're fascinated by this. This is a good way to make bets. That's what probability was invented for, right? It was for gambling. Anyway, so now next time you have 50 people in the room, then you know they share the same birthday. Somebody with someone, they're sharing the birthday.